Section 1.2, functions. So let's just dive right in. We're going to determine if a relation is a function. So what I've given you is a set of points that could or could not represent a function, and our job is to determine that. So one way to do it is just look at the points themselves. By definition of a function, you want to make sure that every single x value is only paired with one y value. So I see a duplication in x's, and the x's that I see duplicating are that 4 and that 4. So all I need to do now is just take a look at it and see if the y's are completely different numbers. If they are, we've got a problem, and it's not going to be a function. So if I take a look at my y's now, I have a -1 and I have a +3. I can say without a doubt that this is not going to be a function. So let's say not a function. Since x equals 4 is mapped to two different y values. Now, if I had a graph in front of me, I would check the vertical line test, which is what is in the written out notes for you. But if I have just a set of points written out, I'm not going to graph it. I'm just going to take a look and see if there's any y's that repeat, or excuse me, x's that repeat and go to multiple y's. Okay, we need to be able to determine just by looking at an equation whether or not it's going to be a function. So a couple ways to do this. I think I'm probably going to graph them, since a lot of people with the idea of determining a function, visual really helps them. So, and maybe a little bit of your prior knowledge as well, hopefully. So this first one I see is going to be a vertical parabola. So I'm just going to go ahead and extract some information here. I know that this is going to have a vertex, and I think I'm going to use this for domain and range anyway, so I won't feel like I'm doing too much extra work, of 2, 3, and it's going to open up because it's y equals, and because of the half in front, I know that this is going to be compressed vertically. So I think I'm just going to take a second and make a quick sketch of that so we can determine if it's a function and the domain and the range. Okay, now that I have a picture of a parabola, and I didn't go through all the steps with that because this is knowledge that we expect that you have carried over with you from last year's math. So now that I have my parabola in front of me, it looks like it is definitely going to be a function, which I expected anyway because it was a y equals parabola. So yes to the function part. And then the next part that I need to determine is the domain and range. Well, the domain on any parabola that opens vertically, so a y equals parabola, is anything. You can plug in anything you want. So the domain's going to be all real numbers. The range, on the other hand, well, this is why I drew the picture. For range, I like seeing a visual representation of it. If I take a look at this, it looks to me like the lowest this thing is going to go is right at the vertex, but it's going to continue up forever. So my range is right at the y value of the vertex, which was 3, and up forever to infinity. Let's take a look at the next one, and I think I'm going to do the same thing. Just do a quick little graph of it as well, and then remember, this doesn't have a vertex, it's got a locator point. So if we identify the locator point, that's going to be the opposite of the bottom, the exact on the right, and this thing has x and y x and y asymptotes. So let's go ahead and get this graph going, and I think I'm going to graph this with you while I'm talking. So -5, -2. So make sure I've got some room to the left and some room down. let's move this up. All right, so at -5, I am going to, so I'm going to go ahead and plot my point right here. There's my locator. Based off of this function, remember that this is where I get my asymptotes, both vertical and horizontal. All right, so now I just need to sketch this thing. So I'm going to go ahead and pick a point or two, plug it in, and just see what happens, and give this thing a quick sketch. So a pretty rough sketch, but I just went ahead and plugged in -4. Plug in -4, and I got the -1 value, and then I went ahead and plugged in -6 and got -3. And then I remembered what these functions looked like, so I just gave it a quick sketch. I also know that, yes, this is a function. Like I just said, if we have a rational like this thing is definitely a function. So yes, it's function. The next thing that we need to do is identify the domain and the range. So this is where the asymptotes come into play. The domain on this thing, you can plug in every x value you want, except the x value of the locator point. So I am going to say all real numbers, x not equal to, well, the x value of the locator point was -5. So I can plug in everything except -5. Range works the same way. You'll get every single y value out of this, except the y value of the locator point, which is going to be, let's see, -2. So a whole bunch of different ways to write the domain and range on these things. These are just common notations that we use at this school. Okay, on to something new. So one of the new things that we're going to be doing this year are piecewise defined functions. So you may have seen these in the past. I don't know how much time you spent on them though, and we're going to be spending a decent amount of time on them. They will be a concept that kind of stays with us the entire year, so first and second semester. So what I want to do is I want to go through and start graphing this thing. But in order to do that, I need to put one of my restrictions back. So it looks like I got rid of the 0 here. So let's put that in. So what I'm going to do is I'm going to go through this one a little bit slower, only because it's the first time you've done something like this, and that's my assumption. So I'm going to take a look at the very first part, and I'm going to take a look at the restriction here. And I'm going to focus on that restriction. Now, one of the ways that I show students in the beginning with piecewise defined is to make a table with it. So I think that's what we're going to do. And then the more comfortable you become with it, you can eliminate the table and come up with a different way to do it. Again, this is just one way that might help you in the beginning. So I'm going to pay attention to that x is less than 0, and I'm going to plug in 0. It's my boundary point. I have to have somewhere to start. So I'll plug that in, and then I want to obey what it says. This is less than 0, so I'm going to plug in numbers less than 0. Now, because there's no equal to part, when I plot this, it's going to be an open circle. If it was an equal to part, like the next one, it's going to be filled in. So now I just plug the values in. So if I plug 0 in, I get 1, -1, I get 2, and -2, I get 5. So off to the side, I'm going to go ahead and start setting up my graph and plot those points. So now when I plot 0, 1, I am going to make sure that it is a whole. So 0, 1, so it's not going to be filled in. And then the other points, go ahead and plot like I normally would. So -1, 2, and -2, 5. Taking a look at this equation, it is going to be an x squared plus 1, which knowledge that I have, I know that that's going to be a parabola that opens up, and it's got a vertex at 0, 1. So I'm going to go ahead and give this a nice smooth curve graph. But I want to make sure I don't go past the boundary. So I normally start at the boundary and go in the direction of the restriction. So starting at the 0, it says that it needs to be less. So I'm going to start at the 0, and I'm going to go less. Yuck. Not looking so good. Let's try that again. Start at the 0, go left. All right, that's a little bit better. Not awesome, but still. Get the basic idea. Now I'm going to do the exact same thing with the next one. So I go over to this one, I'm going to color code this one blue, and I'm going to do the exact same thing that I did. I'm going to make a table, I'm going to plug in the boundary point, although this time this is going to be closed because it has the equal to part in the inequality. Now I'm going to obey the restriction. X is greater, so 1 and 2. Plug those in, and then plot those points. So at 0, -1, it's going to be filled in. Then go ahead and plot my 1, 0 and my 2, 1. Now, based off of this equation, looks like it's supposed to be a line. Start at the boundary. So I'm going to start at the 0, -1, and I'm going to obey the restriction to the right. There you go. I have a piecewise defined function. And it is definitely a function. If you were to go through and test the vertical line test everywhere, it's going to pass. The only time that it looks questionable is at the zeros, but one of them is a hole and one of them is filled in. Therefore, it's still a function. Okay, here we have another piecewise defined. I'm going to do the exact same thing that I did. Again, once you are more comfortable with these, then I would say definitely don't worry about making the table. I know for me, I do it at the table. So I just don't want to worry about making any mistakes on this. So I'm going to go ahead and set this up. I'm going to obey the restriction. Looks like it's going to start at 2, and it is not equal to, so it's going to be an open dot, and then it's less. So I will go 1 and 0. Plug those in, get my points, plot the points, see what I get. So now I finished filling in my table and I plotted the points that I have, but I'm not really happy with this because looking at the equation I know it's supposed to be a parabola, but I'm not seeing as much as I think I'm supposed to. It looks like it's curving, so I can either look at the equation and determine where the vertex is and continue it, or try plugging in at least 1 or 2 more points. So I'm going to go ahead and just plug in a -1 and see what happens. If I plug in -1, I get the 3. So it looks like that 0, 4 is the vertex, which based off the equation, it is. So now, starting at the restriction, I'm going towards, I'm starting at the boundary and obeying the restriction. Sorry about that. There we go. So there's the first portion of it, and let's go ahead and move on to the next one. I'm going to do the exact same thing, so I'm going to pause it. I'm going to fill in the 5, so you might want to pause here too and see if you and I get the same table and the same graph. Okay, so as you can see, I went ahead and filled in my table. You'll notice with the 5, it's greater than or equal to, so I have a little filled in dot next to it, so I know that when I graph it, I fill it in. And then I obeyed the restrictions. Greater than 5, so I chose 6 and 7. Plugged those values in, plotted them, and then I started the boundary where the 5 is, and I obeyed the restriction 5 greater, so I wanted to go to the right. So there's our second piecewise defined function. Okay, another new concept for this year is going to be the difference quotient, which doesn't change. It's always going to be f of x plus h minus f of x all over h. It is an essential skill for this semester, and it's actually one of the things that we come back to at the very end of the school year in like May. So just before finals, we'll come full circle back to this. So at this point, we're just going to be using it as function notation where we plug values in, we follow our arithmetic rules, and combine like terms and just clean it up and just see what we get at the end. So I figure I got a couple of these that we are going to work on together. So, and I think I'm going to color code in the beginning just to make it a little bit more helpful. So off to the right, taking a look at my difference quotient here, this first part, I'm going to highlight in orange, basically tells us just go to the f function and everywhere you see an x, take it out and cram in an x plus h. So I'm going to go over here to my f function. And everywhere I see an x, I'm going to rip it out, and I'm going to cram in an x plus h. And then just make sure you write down the entirety of the function. So take the x's out, we'll place them with an x plus h. Then, the next part, back off to the right-hand side again, we're now going to subtract the original f of x function. So, we're going to, from this, now subtract the entire. I like using parentheses if there's more than one thing, just so I remember to distribute. So I'll put my 3x squared, my original function in here. Then the last thing that I do, and this really is just to kind of finish up the difference quotient, back to the right again, is the h in the bottom. Always make sure that you put an h in the bottom of this thing. Then once you have plugged it in, your job is to just multiply it all out on the top, combine like terms, eliminate some stuff, factor, clean it up basically. So one of the things that I'm seeing here is the x plus h squared. X plus h squared is very common, shows up a lot in these difference quotient problems. So over to the right, I'm just going to go ahead and write down what x plus h squared is. Now, it never changes. It's going to be the exact same thing every single time. So I don't necessarily see the point of multiplying it out every single time. I've just gone ahead and committed it to memory. So, and something that I would recommend you do as well. It's a time saver. No point trying to reproduce it every time. So now I'm just going to go ahead and clean this up a little bit. So replace my x plus h squared. I'm going to go ahead and distribute that negative sign as well. Don't forget the h. Now let's distribute that 3. And then just bring down the rest of it. Don't forget the h. Now at this point, once all of the parentheses are gone in the numerator, you should have things that are going to cancel. Everything without an h should cancel. So let's look. So I have a 3x squared here and a negative 3x squared here. Those cancel. I have a negative 7 and a positive 7. Those also cancel. Taking a look at what I have left over, I have 2 terms still on the top, and they both have an h in common. So I think I'm just going to write down what I've got so I don't lose people. And then I'm going to factor out an h. So you want to actually show that they both have an h in common and that you can take it out from them. So take that out. Once the h has been factored out, now you can cancel the h's top and bottom here. And just write down what we have left over, which is going to be 6x plus 3h. And that's it. That's all we do for difference quotient at this point. You just plug it into the formula, clean it up as much as you can, cancel some stuff out, factor out an h, write down your answer. Some of these can get a little ugly though, and a little bit more confusing just because of the dynamic of the original f of x function. But we're going to do the exact same thing, so I'm not going to let this whole fraction business bother me. I'm going to color code this, I think the same way I did on the previous page. I think I used orange. So now I'm going to go to the original function. Every time I see an x, I'm going to take it out, and I'm going to cram an x plus h in its place. Tried putting the 1 inside the parentheses. It didn't belong there. Then I go to the second part. Now, back over to the right again, I am going to subtract my original function. So I'm going to subtract that. And I'm not going to use parentheses this time because it's only one thing that's being subtracted, and I'm not worried about having to distribute it at all. And then the very last thing is the h. And I think that's what makes this kind of ugly, because we have fractions in fractions, which is just not good. Now, there's a couple ways that you can do this, and it kind of depends on what makes the most sense to you. I don't like having fractions in fractions because I think it's a mess. So I think I'm going to distribute my 3 first. So it looks like I have a 3x plus 3h plus 1. And then, because I don't like fractions in fractions, I'm going to kill the fractions. So, in order to kill the fractions, you need to figure out what the common denominator would be. And then you use that common denominator to annihilate all the denominators. Well, remember that whenever you have multiple things being added or subtracted in the bottom of a fraction, you can't just add something in to make them match. This doesn't make any sense. So the first denominator, 3x plus 3h plus 1, is a package deal. It cannot be split up. 3x plus 1, the second denominator, package deal, can't be split up. And you can't just kind of like tuck things in because you want it to be there. So the common denominator is actually going to be both of those things. So what I'm going to do is I'm going to multiply the top and bottom by what my common denominator would be, which is the denominator of the first one and the denominator of the second one. Now, it's going to look kind of horrific at first, but something beautiful is going to happen, and all my denominators are going to cancel, or all of my fractions in fractions. I'll still end up with one denominator, but not this denominator business. So now what I'm going to do is I'm going to go ahead and distribute. So if I were to distribute this whole thing to my first one, notice that the 3x plus 3h plus 1 and the 3x plus 3h plus 1 cancel. So all I have left here now is a 2 times the 3x plus 1, the denominator that it didn't have in the first place. Then I can go ahead and do the exact same thing for the next one. I'm going to go ahead and distribute this as well to this one. Notice that the 3x plus 1 and the 3x plus 1 could cancel. So now I have minus 2, the numerator, times the denominator it didn't have in the first place. All over, and then this is the part that looks kind of ugly. That big, huge mess with the h and the 3x plus 3h plus 1 and the 3x plus 1. I'm not going to multiply out the bottom. It creates a larger mess and it gets me further away from what I'm actually trying to do with the problem itself. Now the top I have to distribute because there's a minus sign up there. The bottom is all multiplication. That makes me happy. The top, not so much. So I'm going to go ahead and distribute now. Let's see what we get. And hopefully, if I've done this correctly, everything without an h is going to cancel before I do the whole factoring the h out business right before the very end. All right, so let's take a look and see how we did. I see a 6x, good, those are gone. I see a positive 2 and a negative 2, good, those are gone. So I was able to get everything without the h to simplify and cancel. So I'm going to go ahead and just rewrite down what I have. And then from here, it's always a good habit. Your teacher will talk about what steps you can or cannot skip. So at this point, I'm going to show everything. So, factoring out my h. And then once I've done that, I get my h's to cancel. So now I just write down what's left over. I've plugged in everything that I needed to plug in to make sure my fraction bar goes all the way across. And that's the answer to this question. Okay, last example for the notes on the video. There is an example number 9 as well, but that one will be done in class. So we want to make sure that we guide you along with the calculator as well. And you can kind of see the graphing and the hands-on aspect of that one. So this one will be the last one for the videos. And this is just the difference quotient again. So it's practically the exact same thing that we've been doing. You'll notice the difference with this one, though, is that we have an x cubed now. So I'm going to do the same thing that I did with the x plus h squared. I'm just going to write down what x plus h cubed is off to the side. I use it so much, and it's never going to change. So I just went ahead and committed it to memory. So get that written down, and then I can start working on my difference quotient. Now, if you're curious about where this x plus h cubed expansion comes from, it should look pretty familiar. The numbers 1, 3, 3, 1, the coefficients in front, are directly from Pascal's triangle, which I know you used last year. Also, this could be used doing binomial expansion with the whole NCR business with the high exponent, low exponent. So I just don't see the point of having to reproduce it when time is really an issue on the test. I just want to make sure that I can move through swiftly and be confident with what I'm doing. So I just have it memorized. So let's go ahead and plug it in. Do the exact same thing that you've done before. So I'm going to pause now and I'm going to fill it all in. You might want to do the same. Pause now and then start playing it again and see if you and I match. Okay, so using the same color coding that I did on the previous slides for difference quotient, I have my first one with the x plus h plugged in, and then I have the next one with just subtracting the f of x function, again all over h. Okay, so I'm going to do the same thing here. I'm going to pause. I would pause if I were you, and I'm going to fill in and do all of the distribution. I won't combine any like terms yet, but I will distribute everything. So you might want to pause. Okay, so everything is distributed now, and hopefully I didn't make a mistake. So let's see what we can cancel out. So I have a negative x cubed at the beginning here. I better have a positive x cubed somewhere else. Oh, there it is. Okay, so those go away. I have a positive 4x squared, which means I need a negative 4x squared. There it is. Those go away. And then I have a positive x and a negative x. Those go away. So I'm just going to take a second and write down what we've got. Okay, so really going from the previous step where I crossed stuff out to where I've written stuff down now, you got to be really careful about this. The larger that something is when you expand it out, it's really easy to lose a term or two or three. So you really might want to work on your organization, making sure that your handwriting is clear enough so that you can read it, and that you don't try to squish your stuff into too tiny of a spot on the piece of paper. So make sure that you use enough space. I also like to go through and count up how many terms I had and just make sure that I have the same amount. So on the previous line, I see, I'll put my little check marks here. So there's 1, 2, 3, 4, 5, 6. When I take a look at the next line, I better have 6 things. So 1, 2, 3, 4, 5, 6. Good. So I'm going to make sure that you don't lose anything. Now we need to factor out the h. And everything better have an h because we need that h to cancel. If it doesn't, you made a mistake somewhere and you need to back up. So I'm taking my h out of each one of these. And then it's this last one. If you have an h and you're factoring out an h, remember that there's a 1 there. You can't just turn it into a 0. If you turn it into a 0, you no longer have the 6 terms that you knew you were supposed to have. Don't forget the over h. So watch those plain old h's. They can get a little confusing sometimes. Cancel those guys out, and let's just write down what we have left. Once we have this written down, we'll be done with the notes for this section. And then we'll continue on with the word problem in class.